Old.
Hello. Did you get my email?
Yes.
Okay. Is that what you was looking for?
Yes. Thank you.
Okay.
All good. All right. The 60s. Sign everywhere. A sign. Do this, don't do that. Can't you read the sign? I'm going to answer the questions that I left hanging yesterday. See if you can decide, what kind of person are you going to be? So we were scrambling around looking at signs on this. And you may remember I posted this with the correct answer in it, but we were struggling between two answers to this question. Is the velocity in C 2.4 or is it actually 12.08? So let me just talk to you just a few minutes about the concept of signs, and we'll do another example like this. I've always preferred, and I'm actually not trying to talk you into this method because I'm not actually sure it's the best one, but as you know, I'm very much into making sense of things and having it be simple. And so I like drawing pictures and kind of thinking, does that make sense? It would be rotating, to the right and so forth. So we noted in our, let's back up here to this. We noted that this, for C, that its velocity in X was, let's do velocity in Y. We noticed its velocity in Y was going to be 0 because it can't go down. But we figured since this velocity B vector was kind of aiming up over here, that's the velocity of B in Y would certainly be positive, which would mean down here, the velocity of C with respect to B in Y would have to be negative in order for this to work, in order for that to balance, in order for that to actually be 0 as it is, because velocity of C is just going right. So it has to be 0. So we said, well, this has got to be negative. Well, the only way that's negative is if we said this is negative. But then when we took this and put it down here, then it made that rotation negative. And we were like, oh man, that can't possibly be true. So let me just say a couple of things to kind of straighten all that out. Number one, remember, this is a rotationally defined velocity. Remember how that was defined? If something was rotating in this direction, and we said, what's its velocity right there? We defined that as being positive because it's in the direction of travel. So there were rectangular components. Is that the right word? There were rectangular components of motion, but then there was also rotational. And rotational, those velocities were always positive, which means if you're going to do this kind of based on logic, velocity of C with respect to B is positive. That velocity of B up there is positive. Now, in our case, we said it was going right, and so we thought of it as positive anyway. But those velocities, because they're defined as a rotational speed, are always going to be positive. Now, if you want to switch to rectangular, fine. These two blue vectors up here, one is pointing right, one is pointing up. Those are definitely both positive, correct. Down here, same thing. This velocity of C with respect to B has got to be positive. Let's go back here and throw a positive in there. It's got to be positive. But then wait, you say, how can that be? Because if I go right back here, then doesn't that screw this up? Let's see, why can't I erase things? Doesn't that screw this up? Well, the answer is, if you want to take that approach, is that angle right there really 35 degrees? What's that angle really supposed to be called? If you're gonna let the algebra take its course, that angle is not 35 degrees. What is it called if you go that direction 35 degrees? It's actually negative 35 degrees or 225 degrees. Like, you can't use 35 degrees there if you're going to just let the signs take care of themselves. You have to call these angles what they really are, measured from 0. So you'd have to be calling that 235 to 225 degrees. Well, then down here, if you say velocity of C with respect to B times not the sine of 35, I don't know why I can erase that, but the velocity of 225, guess what? The sine of 225 is negative. In other words, the negative actually comes from the sine of 35, not from velocity of C with respect to B. So you can take that approach. I don't like that approach. I like the logic approach. I really look at it. Now, the downside of what I'm saying, though, is if I call this 35, then I have to be smart enough to do what I did here, which is to say, oh, that's negative. So then we wrestled over this, because when we came back here to plug in velocity of C with respect to B, we said, well, you know, what do I call that thing? Is it positive? Is it negative? We were totally wrestling with it. But take a look at the two vectors. In other words, I'll draw these in black, and then we'll move on to an example where we start from scratch. But the components of this velocity of C with respect to V, isn't that right here and right here? That's the two components of it. Notice this one's going right, which is positive, since we are having to do this in terms of X and Y. In other words, as soon as we say we're going to think horizontally and vertically, then we do have to create a coordinate axis and think left and right. So even though the hypotenuse of my right triangle will always be positive, the X and Y components will need to be negative and positive, just like on the unit circle. And then if you go up here, notice your right-hand vector, both of those are actually going right, which means when I came down here, these two components need to be positive. I need to be adding them. They're both pointing right. One's not pointing left and one's pointing right. They're both pointing right, which is why the answer to this is 12, as we kind of thought it would be. We thought 2 didn't make sense, but that's the reason, according to science, why that would be the case. So you're welcome to pay absolutely no attention to signs and let them take care of themselves. However, you've got to call angles what they are relative to 0 and 360. There's no such thing as a 35-degree angle down there in the 4th quadrant. As I said, I don't really know which one's best, but I like to stare at this stuff and draw pictures and so forth, and kind of think, yeah, it would rotate that way. So let's take a look at one more problem like this, except rather than just sort of immediately do it for you, I'd rather give you a little bit of time to think about it. Probably not enough, but a little bit. Because I do want to take our time with this topic. I'd like you to get it. I'd like you to feel like you can think. That's one of the things I'm always interested in, is don't give up thinking. And that's why I like just reasoning it out and drawing pictures and so forth. So this time we've got the driver up here driving to the left. Again, right off the bat, we're already faced with a sign issue, like, oh, it's left. So do I call that negative or do I call it positive? Think about that. So that's driving left. And so, of course, that's going to cause this to move in that direction, which means B is going to kind of rip around that circle. And remember, it's just following the dotted path. I drew that as a dotted path because it's not a real object. That's just the path it's going to follow because of this arm right here, this metal arm. So it's going to go that direction. Let's also just think about this for a second more too. So if this actually goes in that direction, would you agree that the new location of this connecting rod AB, would you agree that A will move to here and B will move to here? So that's what's going to happen to it. a second later. So if that's the case, what do you expect omega to be here? Is that a positive or negative number?
Positive.
Yeah, that's counterclockwise rotation. So that's actually going to be positive. I better get a positive number for that. Now, again, that's the downside of thinking logically, because I'm just looking at the picture, trying to figure all this stuff out. If I kind of just ignore all that and just use, I think it would just come out natural and you wouldn't have to think about it. So, okay, that makes sense. So that's going to rotate like that. That's what's happening. See other things going on. Just in terms of labeling these, because we've only looked at this once. Does it make sense? Perpendicular right there. That's what the velocity of B would be. And we said a second ago, that's going to be a positive number. But the thing I wonder, that's kind of the easy part. The hard part of this, I think, to visualize all this is, where is the velocity of B with respect to C? Where does that go? In other words, remember, we broke this into two parts. In this case, A is moving B, and we kind of want to know what's happening at B. So our equation is the velocity of B will be the same as the velocity of what A is. And that's the translation. But then the rotation, which is how, I think I wrote the wrong letters up here, how the velocity of B with respect to A as it rotates around A. Should have been an A and not a C. That's our guiding equation for these things. And again, my question to you is, can you see that happening? If you can, then you're going to be able to tell me where to draw the vector V of B as it rotates around A. If you don't understand that, you're not going to be able to draw it. And I find that hard. I find that challenging. I don't know if you do. So to reiterate from yesterday then, the first thing A is going to do, because I just showed it doing both at the same time. When I showed it rotated, I showed them both at the same time. But if this is the case, would you agree that that's what happens first? Or velocity of A. In other words, if A moves to the left a little bit, B is also going to move to the left a little bit. That's first what's going to happen, right? But then what happens, because B can't move out there, right? It's connected to C, and like it can't do that. It's not going to be allowed to do that. It's got to be forced to follow that dotted path. So what does it have to do second?
It has to move down.
It's got to rotate, kind of rotate into position. In other words, and you're exactly right, down. So if this point is sitting right here, so there's A prime, in other words, it's kind of moved to the left a little bit, then can you see that this is actually a rotation in the sense that it can't slide straight down because A can't move down. It's sitting inside this piston, and so A has to stay where it is. So how's B going to get back on track? Well, it's got to rotate. So it's going to have to rotate down into that position. And so now everything is fine. And that's why this equation works, because we say first there's a translation where it slides left. So whatever velocity A is, that's the velocity B will have. But then there's a rotational velocity to get it back to where it's supposed to go, because it's actually got to be following that circle. And again, this happened kind of simultaneously, like you can't see them. But see what that tells you right there is which direction it's actually rotating. It's kind of going this way. Does that make sense? That's the velocity of B as it rotates around A. That's where it is. So again, it's rotating. Well, we saw it a second ago. It's rotating in this direction. That's its rotational. So the question is, can you see that? Can you slow down, draw that out, visualize it? if you can, then you can actually do, now I'm gonna have to, because this really can't go where I just said it went. You have to see this arm. It's a little bit more. Let's go blue. You have to see that this is the radius. It's rotating around A and it's rotating at B. And remember, just like this was perpendicular, to its radius, well, so is this up here. In other words, I got to take off like that. Perpendicular. That is the location for B as it rotates around A. So notice, in a sense, I haven't drawn anything as having moved yet. But it's the combination of those two velocities, the green velocity and the blue velocity, that's actually going to result. I should say the A velocity moving to the right. Up here is the velocity of A. So what you want to know, of course, since A is the driver, is you want to know what it's going to do at the other end, because we're studying, connected shapes. We're studying velocity as it applies to, objects that are relative to each other, relative motion analysis. A moves, and because it's connected to B, then B is going to move too. So we want to know what's happening at B. So it makes sense logically, even without having a note sheet, that I would be having V of B over here. I want to know what the happenings to the velocity of B. And we say, well, it depends on what A is doing and how B is rotating around A. That's the basic conceptual underpinnings to how this works. So the hard part about this is, can I draw this stuff without kind of screwing up what I'm looking at so much that I can't even read it, can't even see what's going on. So I'm going to go back and kind of get rid of some of this. So what I want to see if you can do then is, armed with that knowledge, and I'll give you a second to think about this, can you draw the horizontal set of equations? And can you draw the vertical? And just write the equation out. Don't plug anything in yet. Can you just write the dumb thing out, and then we'll see what we can plug in and what we can actually solve. So I rewrote the blue equation, but focused on X for horizontal, focused on Y for vertical. So now the question to you is, what can you plug into those?
Well, we already know we're doing A. So VAY is 0, and then VAX is, well, theoretically -5. It could also be 5, depending on how we want to set it up.
Yeah, I think it probably is easier just to leave the x-axis right as positive, left as negative, but you actually are more than welcome to say, hey, I'm going to aim left and call that positive. I'll stick with the convention. So notice what I hope you would see right off is that the velocity of A in the x direction, I can know that right now as being -5. And because A is constrained inside its cylinder, the velocity of A in the y direction is nothing at all. So there's some things I know for sure. And of course I know those because I know what's happening at A, right? I know what's going on at A. I just don't know what is going on elsewhere. So the instant in time here is when theta is 32 and phi is 38. So I got to get that involved because that's it. Like that's all you know. You're done right now. There's nothing else you know. And that's 2 equations, 4 unknowns right now. So this is not good.
Well, we have the direction that B has to be moving at this instant by just finding a line tangent to the circle.
That's correct. And let's take a closer look at that. Since that green vector is perpendicular to BC, which I didn't draw very good, looks a little more than 90 to me. I could kind of draw in, let's see. You can't do any of these problems the same. You just got to play around a little bit. Let's see. So here's one way to do it. If this angle theta, which we were told was 32 degrees, if that's 32, then isn't this angle up here also 32? And since this is 90, then that angle right there would be 58 degrees. So remember, velocity of B is positive, but its velocity in X, the velocity of B in the X direction would be negative. And the velocity of B in the Y direction would also be negative, wouldn't it? And I can know those based on the velocity of B. Now here's the cool trick to this, because you don't actually know anything here. But the velocity of By would be the same as the velocity of B, but modified by the sine of 58 degrees. Now again, in my case, I have to look at the drawing and go, dude, that's negative. I got to throw a negative sign in there. But if you say, you know what, I'm not going to call that angle 58. I'm going to call that angle 180 plus 58. I'm going to call it 138 degrees. Then I can just take the sine of 138 and the negative will happen automatically. Do you understand that? I don't care which one you do. I like drawing pictures, visualizing it, and so forth. So I'm going to make some dumb math mistakes because I'm going to forget to assign negatives and so forth. And then even assigning negatives is a little weird because, you know, like, do I write negative in front of that, or do I just say to myself, when I'm all done, velocity of B there must be negative? You see what I'm saying? That's kind of that's a weird part of the sign aspect of this. I'm going to throw a negative in front of it and we'll see what happens. And then the velocity of B in the X direction, the same exact thing happens, which means I say, well, that's the same thing. It's the velocity of B, not the velocity of Bx, but modified by the cosine of 58. And then I notice in my picture it's going left, so I'll give it a negative sign. Now, do you see what just got accomplished there? I'm not sure why it's got the computer. I think you guys can still hear me, but it seems to.
Yeah, we can still hear you.
Seems to, like, the video just shuts off randomly during discussion.
Yeah, now we should be able to solve it now. Two equations, 2 variables. Or no, shoot, we have 3 still. Almost.
Yeah, you're exactly right. We're almost there. We have. We got it down from 2 equations and 4 unknowns to 2 equations and 3 unknowns. But the question is, can you do the same thing with the velocity of BAX and BAY? Could you rewrite those as just the velocity of BA without an X and the velocity of BA without an X, except for modified by the sine or the cosine or something of that nature? Could you do that so that try that?
Oh, what is the angle of phi over there?
That was 32.
Okay.
No. 32. Wait, did I screw this up? 32. 38. There we go.
38.
But isn't your gut reaction to that this angle up here being 38 kind of isn't very helpful because it's like way up there? Like, what good is that going to do me? My velocity of BA is down below, so it's like, how's that going to do me good? Like, why'd you even tell us that? There's more than one way to do
Yeah.
this, but here's something that you could do.
Should be negative 50. Oh yeah, you can just draw a horizontal line kind of through B and then
That's exactly right.
break up the 90-degree angle.
That's right. So I have a 90-degree angle here, but if that angle up there is 38, then that means this angle is also 38. Isn't that true? So this would be my velocity of BA in the X direction. And this would be my velocity of BA in the Y direction. And since that angle is 38, that means this angle inside here is 52. And so the 52 is the one I'm going to use. So couldn't I then say that the X coordinate is the velocity of BA times the cosine of 32? And notice it's positive, it's pointing right, so I'm going to leave it positive. The velocity of BA in the Y direction is modified by the sine of 52, which I need to notice is down. Now, the fact that I put the negatives into this basically means if I solve what now just became, instead of 2 equations, 4 unknowns, it just became 2 equations, 2 unknowns. If I solve these 2 equations, 2 unknowns, I'm going to get positive answers for V of BA and V of B, because there's no such thing as a negative velocity. I added the direction myself based on my picture. So if I didn't screw this up, those 2 numbers will come out positive on their own. So we've solved a lot of 2 equations, 2 unknowns. So I look at this and I think that's sort of terrifying. So I'm going to use a matrix. And so this will be my kind of V of B numbers, and this will be my V of BA numbers, and this will be my number itself. So I have negative cosine of 58 for my coefficient up above. I have to subtract this to the other side, so that would be negative cosine of 32 if I moved it to the other side, and the 5 is already on that side as a negative 5. Now I got to be consistent down below. What do I have for the second equation down below? Well, I've got a negative sine of 58. It's already on the left side of the equal sign, and I'm just going to leave it there. This one is on the right side of the equal sign, so I'm going to have to add it to the other side, which means this is actually going to turn into a positive sine of 52. And then I've got a 0 over there. So there's my 2x3 matrix that I'm now going to stick into my calculator. Second matrix. I want to edit a 2x3 matrix. I'm typing in negative cosine, I'm in degree mode, of 58, negative cosine of 32, negative 5, negative sine of 58, sine of 52, did I get excited and screw up here? 52. I think I wrote 32 right here. That was a mistake, wasn't it? Suddenly was looking at my angles thinking they're not all the same. That was the cosine of 52, not the cosine of 32. I was just thinking I had 2 angles. How come I have 3 angles down here? So sine of 52, 0. So now I'm just going to go back to that number and type negative cosine of 52. I think it's fixed. Second matrix.
Why again are we using like cosine and sine of 58 instead of like the sine and cosine of 32? Because it's the same values, but like why'd we take the 90 minus the angles that we were provided?
Only because the right triangle is actually, below. In other words, because it's down here, I need the angle that's in the triangle, not the one that's not in the triangle. If this angle's 52, then this angle over here would be 38. Does that make sense? So again, I'm taking the slow approach, I guess you could say, by drawing, I actually wanted the angle sitting in the triangle. So, here's my right triangle. I need an angle in that triangle if I'm going to use trigonometry. So I use 52. If you use 38, you got to be careful because 38 in the triangle is actually this one over here. So if you say the cosine of 38, you're not going to get X, you're going to get Y. So I did that, and true to my hope, I got positive answers to both of those, which makes me happy because I sort of knew that darn well better happen. So if I didn't screw up, I got the first column. I got velocity of B is 4.193. 4.19 is probably close enough. So velocity of B is 4.19. Forgot what my units are. I'll go back and look at that in a second. My velocity of B as it rotates around A is 4.51. So they're, really similar numbers.
That matches my calculations.
You got the same thing?
Yep.
Good. So basically now if I look back at my picture, I literally know the velocity of B, because that's one of the questions that, you know, I'd want to know, which has to do with a linear speed. That's the linear speed of point B as it's rotating. But then there's also the angular speed, B of B, as it rotates around A. I mean, both of these are the same. Basically, this velocity here is what happens when this point rotates around C. So this point moves, it rotates around C, that's how fast it's going. But it's not just doing that. It's also causing this radius right here. This bar from B to A is also rotating around A, and that's got its own separate velocity. And so there's kind of two linear velocities and two angular velocities. And now I can just use my conversion factors, since I know that generically all linear velocities are converted to or proportionate to their angular velocities by just multiplying by the radius. So let's see, what were all these? This is feet per second. So these are feet per second. I should go back and add that. So I say, cool, well then the velocity of B, 4.19, would be equal to its angular velocity of B. And notice B is doing what? It's rotating around C. So you don't have to say this, but it's just kind of cool to say it. Just tells me what, it just reminds me it's rotating around a point. B is rotating around C. And also reminds me, what radius do I need? I need the radius of BC, which I was given at the start of this, is 2 feet. So basically I can see now that I'm just dividing 4.19 by 2. 4.193 divided by 2 is 2.0, 2.1 really. So the angular velocity, notice its units, and I mentioned this yesterday, but let's just go ahead and stick all of those in here. This was actually 4.19 feet per second, and then we went and divided by 2 feet. And so our unit for this is nothings per second, because the feet actually cancel, which means it must be in radians. And so it's kind of interesting to think that radians are the natural way of measuring angles in the universe. So as a result of A moving and being connected by a rod to B, I actually know how fast that thing is spinning around. I mean, that's kind of cool. And can you appreciate, as a motor system, which is what I tried to introduce this to you, that linear speed of 5 feet per second, at least at this snapshot in time, is producing an angular speed of 2.1 radians a second. So that's just kind of cool to understand. I mean, I know how fast that's rotating down there. I mean, the whole reason I did this was to create rotation and so forth. So it's like to understand what's happening here, really powerful. And then similarly for the other question, I've got the exact same math. Well, not quite the exact same math, but because the big difference, of course, would be now we're talking about the angular motion of B as it rotates around A. Therefore, the radius is B to A, which you can tell from the picture is much longer, and that's 6 feet. So you're going to get a much smaller answer since this is 6 feet. So the rotational speed of B as it moves around A, 4.512, 4.512 divided by 6 is only 0.75 radians per second. And again, I haven't even really read the question. Is that what it was asking? I don't know. I'm just figuring out everything I could possibly figure out about it. So notice B is actually rotating pretty quickly, but at least as it rotates around C, but the rotation of the rod, and notice what the two things are really talking about. I'm not going to get rid of all this stuff just because I don't want it to be gone for the notes, but you're really talking about the two kind of metal rods in this situation. Here's one of them right here. You're basically talking about how fast is that spinning around. But then we saw in my Desmos that this thing was also kind of rotating, but it doesn't rotate as fast. So I just wrote those down. Are those, did the signs take care of themselves? Are those speeds both positive, meaning they're both, did that happen naturally? Like this one's going this direction and so is the other one? That's positive, right? They both came out positive. If you think about it, is that the way they're really rotating? Do you agree with that? Did we get lucky? Would they have come out negative if they're supposed to be negative? Do you see them as rotating positively? We'll notice B is going this way. So isn't that going to certainly cause this arm to be going that way, which is positive rotation? So I don't have to change that. Maybe again, I got lucky, or maybe the signs would have taken care of themselves, but that's definitely rotating that way. And we saw a second ago, or I guess we could even see it right here. I mean, if velocity of B over A is going this direction, then doesn't that also mean, as we said at the start of this is going this direction too? So they're both actually rotating positive here. So I didn't have to change those. So tell me something about yourself. Is this settling into your brain? How are you like, I got it, but I need more time to work on my own. I got it.
Do we
But,
have a homework for this?
mhm.
Okay, then it's all good.
Yeah, it's a little confusing now, but like after doing it a few times, it should make sense.
Yeah, and I want to
Simple.
caution you because notice we're only talking about velocity, but in a later section, which won't happen today, we're going to say that this not only has a constant speed of 5 feet per second, but we're going to come back and say, and it has an acceleration of 2 feet per second. In other words, it's actually speeding up, which of course is fair in the sense that, you know, does A have to be moving to a constant speed? Can it never accelerate? Well, no, motion can include acceleration. Well, if that's the case, then what happens down at B? Can we find its speed and its acceleration as a result of this? And that's going to take this to, we're going to have to learn anything new, but it's going to take us to another level. It's like, if you think this is confusing, this is actually going to get worse. And so I'm only saying that to say, if you practice this stuff now so that you can do it, then you won't have any trouble with that. But if you don't and say, well, I'll just wait to do my homework till later, it's probably going to feel a little piled up on you. Notice what just happened here. As I said, we quite easily wrote out 2 equations for unknowns, but then that substitution got it down to 2 equations, 2 unknowns. Well, the problem is we're going to have like a whole nother set of equations for, like, these are the velocity equations we wrote. We're going to have a whole set of equations for acceleration. And if we write them out, we'll end up with like 4 equations, 8 unknowns. Like, that's what's going to happen. We're going to have a horizontal acceleration equation, a vertical acceleration equation. So we'll have 4 equations, but they'll just be unknowns everywhere. And so your ability to kind of write that out and not get lost in the process of how to tackle that is really good algebra training. But my point is, you want to get this down now so that when we bite off more, it isn't as terrible as it could be. Let's see. Actually, I never really read the question. It said, find the angular velocity of link BC. And that's it. So we actually sort of found more than we needed. Now, did I need to find everything? BC. So that was this one. Whoops, that's not right. That was this guy. We sort of didn't need to do the second one. So could we have sort of stopped a little sooner someplace? Well, maybe. Now, I'd like you to notice one thing about this question. Like if you read the question, do you notice there's like something I kind of ignored there? We just kind of did it. But what the heck is this? Did you read that and think, I don't know what that is, but whatever. Just kind of pretend it's not there. Find the angular velocity of length BC using the concept of ICR, instantaneous center of rotation, is what that means. And we now know the right answer to this question. We did it one way, but I'm actually going to show you a totally different way that's really kind of neat. I think you'll just appreciate this. So the good thing is I'm not really teaching you anything new. Like we know the right answer to this question. It was link BC, and we got, was it 2.1 for that? And so the question is, can we get the same exact answer? Let me make sure this is a good question for this. Got to make sure that the first question I show you this with is nice. All right, let's take a stab at this. Would you agree with me that since the velocity of A is ripping to the left at 5 feet per second, that it could be thought of as kind of, I guess you could say, some, like, let's say it's rotating around this point right here. Like, isn't that how velocity works? Like if things are, now in our case, it can't rotate in a curved fashion, but at least at that instant, would you agree that A could be thought of as kind of rotating around this point down here? You see what I'm getting at by that? Like that's how velocity worked, right? In other words, we had a circle, we had some point over here cruising along in a circle, and we said, what's its velocity? And we said, oh, it's perpendicular. It's tangent to the curve, which is sort of perpendicular to kind of the center, right? In other words, the center of the circle on which it's cruising around on. We said if we knew where that center was, then the velocity of that point is always perpendicular to that radius, right? Does that make sense? Now you might look at that and go, well, yeah, whatever. I don't get where you're going with that, but that is true, correct? And the problem is, I do know the center could be thought of as being here or here, like anywhere. I don't really know where to put it. Does that make sense? But I could think of it like that if I wanted to. You agree with that? But now let's do this again with point B. Would you agree? We know for sure because B is being forced by the mechanism here, the mechanism A, B, and B, C. It's being forced to stay on that circle. And really it's being forced to stay on it just because of the radius BC. And so isn't this the velocity of B? As we said a second ago, this is the velocity of B. And that red one is the velocity of A. And so would you further agree then that we know it is actually rotating around point C, but the interesting thing here is, at least for this second in time, instantaneous, this instant in time, ICR is instantaneous. center of rotation, ICR. That at least for this instant in time, they're both actually rotating around that exact same center. Do you agree with that? They could be thought of as doing that anyway. They're not, because A can't rotate, right? It's got to go straight. But at least for this instant in time, they're both could be thought of as rotating around that center. You agree with that? Does that do any good? What's the purpose of that? Or like, why would that help us? I'm just going to call this I for a second, since that's an easier letter to write.
You find
Well-
how much of that 5 feet per second, how that translates to rotating around our little circle. We know that the same velocity has to be experienced on the other end of the stick.
Yeah. So what this is I can see that this rotation of A as it rotates around I, that's going to rotate. But then isn't this also going to rotate? In other words, this omega as B rotates around I. Well, it turns out those are equal in this case. That's what's so cool about it. Now, the velocity of B won't equal the velocity of A. They don't have the same exact number. They're not both 5, but their rotational velocities will be the same. That's what's so cool about choosing the exact same center. They have identical rotational velocities or angular velocities. So now all we have to do then is like figure out some of that in this picture. Now, in the end, this is not some amazing method that suddenly makes everything easier. You have to do different math, but you might find that this different math is easier than the previous math. Or you might find it's worse. But we're actually going to get the same answer here. That's the thing that's kind of cool. Well, what things do we need to know? In the end, we have this triangle here, the triangle that's created with A to B and now to I. We have this triangle, and it's very typically going to be a non-right triangle. But that's okay, because we have the law of cosines and the law of sines that we can use to kind of figure things out. If you have a program in your calculator that does those for you, you're more than welcome to use it. So that's kind of cool. And notice you do know some things, like, you know, AB is 6. Like, isn't that distance is 6? Do I know any angles in that triangle?
We can pretty quickly find one because we can because we know theta and phi. We can
Yeah, so-
find the interior angle on ABI, I guess.
Yeah, like which one do we know? Like which one?
Yeah, the easiest will be the one from A, because it'll just be 90 minus phi.
Exactly right. Like, don't we say that this angle here has to be 90 degrees? And so if phi, we are told, is 38, then doesn't that force this one to be 52? So I know an angle in that triangle pretty quickly. I didn't know any, but I know that one.
Yeah, and it gets a little bit easier from that point on because the two lines have to be the same length. The I guess two dotted lines in the picture here have to be the same length for the circle to work out. So we also note the other angle has to be 52 as well.
That's a good question. Is the other one 52? Let's
Well,
see if that's
necessar-
true.
I think necessarily it has to be, right?
Would seem like it. So this angle up here was 38. We said a minute ago this one would also be 38. And if this one down here was considered to be 32, then this one's also 32. You agree with that so far? So I guess that overall angle is actually 70 degrees, isn't it? And so 70 and 52 is 122 minus 180 is 58. So this angle down here would be 58 degrees. Is that true? Yeah, that is true. So it turns out, despite your extremely logical thought there, it turns out that in order for two of those sides to be the same, two of the angles would have to be the same. In other words, in an isosceles triangle where this length is the same as that, these two angles down here are the same as well. So you have to have two angles that are the same in order to make two lengths the same.
Yeah.
So oddly, they don't even have to be the same length, which is kind of crazy, but
It feels like it shouldn't allow them to land on the same like arc of a circle if we consider I to be them.
so the key to what you're thinking, Landon, is if this is not the instantaneous center of rotation, it's the permanent center of rotation. In other words, if those two lengths were the same, in other words, this length over here matched this length over here, if that's the case, then
Oh god, yeah, gotcha.
this would actually be 5, just like the other one is, and that would be the permanent center. So the cool thing about instantaneous center of rotation is if you let 1 second go by, that eye moves to some other location. It's not there anymore. Let me show you what I mean. In our case, my drawing just sort of worked out that the green and the red look the same. But if this goes to here, which means this velocity of B just moved to there, does it make sense that the new instantaneous center of rotation is there now? So that instantaneous center of rotation is actually moving constantly. So the question is, what else do we know? Like, we know all the angles. Well, and we know one side. So we're actually on our way because of, let's see, would that be the law of sines or the law of cosines? Or does either one work? How good are you at those two formulas?
We don't know the lengths of the green and red lines, so I think we need to use law of cosines here.
It turns out that the law of cosines includes all three. Do I still have this note sheet here? Yes, there it is. The law of cosines includes all three sides, which is fine as long as you know two of them. But you can't have an equation that has two unknowns in it. We only know one side. And so that means if we use the law of cosines, it's going to have two unknowns in it. So it's not that it won't be true, but it's actually not going to help us. So I need to know two sides in a triangle before the law of cosines is going to work. I'm going to have to use the law of sines, which is actually good news because the law of cosines is easier. I'm sorry, the law of sines is easier. So the law of sines says the sine of any angle, I'm going to pick 58, divided by the side across from it. And that's why I picked that one, because I need to get the 6 involved, right? Would be the same as the sine of any other angle divided by the side across from it. And so the side across from 52 is the length BI. So I'm going to call that BI. And that would also be the same as the sine of the other angle, which is 70, the sine of 70 divided by the side across from 70, which is from A to I. And so, and I don't know how well you remember trig, but if you're hunting for an angle, taking inverse sine, there's a danger of the fact that there could be two different angles. But in this case, I don't really have to worry about that. So I've got a program in my calculator called, actually, I guess I don't have a program in calculator. So this isn't hard. I'm going to kind of cross multiply. So if I take sine of 52 times 6, I'm assuming with as much math as you've had, I don't need to show you any algebra here, divided by the sine of 58, that I get BI pops out as a distance of 5.575. And if I do the same thing, except replace 52 with 70, then I get, putting these two together, I get AI as being 6.648. So I solved the triangle, meaning I know all lengths and angles now. I know the radius, AI. So let's think about this equation then. There's kind of more than one way to do this now, but let's just think about this. If I grab this equation up here and bring it down here, and I kind of add to it the fact that V equals omega times R, or I guess that would mean that omega equals V divided by R, then couldn't I say that the velocity of A, so I'm just taking omega here, if this is omega, then wouldn't that be the velocity of A divided by the radius of AI? Isn't that the same as, well, this one here, omega, I'm just looking at this here and saying, well, that's equal to V over R. So that'd be the velocity of B divided by the radius of BI. And actually, I know all those things now, don't I? Well, I know lots of them. Again, I'm a little concerned about signs all of a sudden. In other words, if I just go in here and throw a 5 in there, since it was 5, do I need a -5? Well, think about that. AI was 6.648. BI, the radius from B to I, was 5.575. I don't really care how far to carry that on. I just pick that. Well, notice that's an equation with 4 unknowns, and I know 3 of them. So cool. So if I take 5 times 5.575 and I divide that by 6.648, I get the very satisfying result that the velocity of B is 4.19. Why is that very satisfying?
Confirms the previous answer, right?
Yeah, isn't that what we just got a second ago? That's the same exact answer. That's pretty cool. Isn't that weird isn't that a brilliant idea? Who thinks of these things? Would you agree though that wasn't any less work? Like there's still tons of work to do. It's just like different work. Like, are you a triangle lover? Do you find yourself confused by, this business of which direction is everything pointing? The fact that I had to look at this and this one wasn't too bad. In other words, establishing the velocity of B perpendicular to its radius. But this one here, that's a little tougher. You know, it's a little tougher to see. And by the way, I had to think a lot to even know it went this direction and not that direction. How do I know the velocity of B? How do I know it's not rotating in that direction? I had to play with that a little bit to know that for sure. Had I got this going the wrong direction up here, does it make sense that would have created a totally different right triangle than the one that I used down here? So you can't just mindlessly draw that in. I mean, you got to really think about which way that thing is going. So if I was to try to, you know, make an argument that this was better, it would be based on how confusing that can be. Now, remember, velocity of B is a positive number. So notice I kind of said, well, should I be throwing a -5 in there? Well, in this world, we're thinking of this 5 as rotating around a point. In other words, the 5 actually is positive here. Do you understand that? Because we're saying, hey, everything's rotating here. There isn't any linear speeds. They're all rotational speeds. So that 5 is 5 rotating around I. Well, that's positive because it's going in the direction of its rotation. Velocity of A is 5. Velocity of B is positive. It's always positive. So now, again, this problem didn't ask for velocity of B, though. It asked for the angular velocity of link BC. So how do I get that? Well, no different than what we just did a minute ago. In other words, I just figured out that the velocity of B is 4.19. And don't we have this formula that converts that for us? I just have to use, since we're asked for the angular velocity of BC, not BI, because remember, I doesn't exist. It's nowhere. Like we placed it over the top of this just to try to figure this out, but that doesn't actually exist. And remember, even if it did exist, 1 second later, it's not there anymore. It's not like you can say, oh, good, look, we know how far BI is. Well, BI is going to be different 1 second later. Those links are, it's all going to change. This is all about the instant. Everything about this has to do with the instant. So then I go back and say, okay, well, the angular velocity BC, well, now that I know this, I can say, well, since V equals omega times R, I can say, well, then if I know 4.19, and I know the radius of, well, notice you got to think a little bit more since they said omega of B as it rotated around C, you know, then this tells me, oh, okay, I need to replace this R with the radius of BC, which hasn't changed. That's still 2. I mean, this is the same thing we did on the other page, but the point is that the thing that this produced just wasn't what I was asked for. And so I just had to do a little bit more work. So the point is I get the same exact answer I had before, which was 2 point something or other. I don't remember what. .1 we said before, 2.1 radians per second. And notice that's all this problem asked, which means I could just say I'm done and don't have to find anything else. So that's kind of cool. See if you can do that for, well, this question. We're going to run out of time for this. So whether this last section is a little weird in the sense that it's not just going to neatly fit into each day. Like it's going to take us a little time to maybe do some of these problems. So I don't know. Let's see what this guy looks like. Yeah. Notice this is a good question to do next, because do you see what the driver is here? And this is a much better picture of what would really happen. What's the driver in this case? Who's driving who? This is always linear connected to rotational, because that's the way combustion engines work, and it's such a powerful part of our culture, our economy. But notice you're told omega of B as it rotates around A is 3, positive 3. So since it's positive, then B is effectively the driver, or AB is the driver. And so this is going to cause motion in C. And of course, since it's rotating that way, perhaps you can logically see that C is going to go this way. But I'm wondering, can you draw the picture for this? Can you draw it roughly? Just going to give you a second to think about this. Do you understand how to find this center thing? Because it really comes down to the fact that velocity of B is the driver, and velocity of C is kind of the follower in this case. And it's those two velocities that you got to draw in. Well, notice I just drew in velocity C. And the only reason I know that is because it's constrained by the kind of the tunnel or the cylinder that it's in. Where's velocity of B? You should be able to draw that in rather quickly, I hope. Perpendicular to AB. That would be the velocity of B. How do you find? So those are the two relevant velocities here. Point B is moving with a velocity. Point C is moving with a velocity. V is causing the motion. B is causing the motion. C is resulting from the motion of B. How do you find the instantaneous center from this? What do you do? Somebody put that into words.
Find the point that they're both rotating, the common point that they're rotating around at this exact moment.
Yeah, and where do I look for that? What do I draw in here to find it? What's
Make a
true?
triangle between C and B and have the lines coming out of C and B be perpendicular to their current velocities.
Very well said. The center of rotation, if C is going to be thought to be rotating around a point, then the point at which it rotates has got to come off perpendicular, so it's somewhere along that line. What's true about the other one? Same exact thing. I got to take off perpendicular. It's somewhere along that line. Well, the only point that works for both of those at the same time is where those two hit. And I'm given BC is 56 millimeters. So I know that length. But I need to know that, again, this is a non-right triangle. I need to know some angles in this. And so can you use phi and theta to figure some of those angles out? Again, some of those are easy. Since phi, of course, is 24 and this angle down here is 90 degrees, that certainly leaves this angle here to be 66.
Is
So
angle I 40?
What do you say?
Angle I is 40.
40. Why do you say that?
Because pretty
Brilliant.
much the same angle as A.
That's exactly right. That's exactly right. Sometimes you'll do this the hard way and sometimes you'll do this the easy way, but do you understand what Evel just noticed? Like this is coming down and this is horizontal. Well, isn't this coming down and this is horizontal? So those are what mathematicians would call corresponding angles. I'll erase this, but if you have two parallel lines and a line that cuts through them, these two angles are going to be identical. So we got lucky in this case because these two angles were actually parallel. Does that make sense? They're both level. So, and those are going to be identical. So Evold found the easy way to get that other angle. Is there other ways? Absolutely. There's all kinds of ways. You could spend quite a long time. This is not a race. Like just get the dumb thing figured out. So now that I know those add up to 106, I guess that leaves 74 for this top angle up here. So we'll have time for this. You take it from here. We'll finish this right now. Can you do the math? Because we're going to need those two radiuses that we didn't know. So this radius CI over here, we're going to need to know that radius. And this radius BI over here, we're going to need to know that. Can you do what is necessary to pull that off? And I think it's going to be a common occurrence that we only know one of the links in the triangle, because those two radiuses we're never going to know. So I think these problems, it seems to me, would always be law of sines. I'm just going to give you a second or two to try to beat me to this.
Do we have to convert it to meters?
Not necessarily.
Okay.
I don't think so. So it is an important point to point out that the velocity of B would be equal to the angular speed of B as it is forced to rotate around A, as long as I multiply that by the radius of AB. So since I know the angular speed is 3, notice the unit, radians per second, multiplied by a radius of AB, which we were given is 17 millimeters. Since a radian is really unitless, if I multiply those, I get millimeters per second. So I guess velocity of B is 51 millimeters per second. I'm lazy, so if somebody doesn't make me convert it, there's nothing saying the speed can't be in millimeters per second. So that's that velocity. So similar to what we had before then, I could say that the sine of 40 divided by the side across from it, 56, is the same as the sine of 66 divided by the side across from it, which is BI, which is the same as the sine of 74 divided by the side across from it, which is CI. And so using that, I could find these lengths. That gave me BI as 79.59, which would be millimeters. And if I retype that in my calculator, replacing the sine of 66 with the sine of 74, all the math is the same, and I get 83.745 or 83.75.
Yeah, that's quite match what I've got. Let me double check.
So since we're out of time, I'll speed up a little bit by just not, so their omegas will match because they have the same exact center. Since the top one is 3, well, that's not true. That's 3 from AB. What matches is omega around this point, like omega of BI will match omega of CI. I should have put CI down below. That was C moving down there.
And then we can just divide by the radius from A, well, technically B, and then multiply by the radius to C.
That's exactly right. Since I converted and found the velocity of B, remember since those are equal, then I can really say that the velocity of B divided by the radius, since that's what omega is velocity divided by radius. So
Michael Williamson.
So I can say the velocity of B divided by its radius, which is, I think I'll write this in here just for the sake of the notes, divided by BI. That's going to be the same as the velocity of C divided by its radius, CI. And again, I know all of those things. Well, at least I went to the trouble to find the velocity of B. If I hadn't went to that trouble, now I would see that I need it. And I know these two radiuses now. So I don't know if that's the final answer, but it allowed me to move the velocity of B, which was the driver, down to the velocity of C. That's what the beauty of this whole system is. And so I end up with 51 times 83.75 divided by 79.59. So I get this proportion. I get approximately 53.7. Hence, the velocity of C is approximately 53.7. And our speeds here were in millimeters per second. So I didn't change that. I didn't see that I had to any place. If that's what it asked, then I'm done. But it says find the velocity of C. Yeah. Done. Notice it doesn't make any sense. Why would it not make any sense to go find the angular velocity of C as it rotates around I? Why would that not make any sense to be asked to do that?
I is just something we're using to
Yeah.
kind of as a calculation tool. It's not really
Yeah.
anything.
Yeah, it's nowhere. It's not in the picture anywhere. It would make sense to say what's the rotational speed of B around A, because that's actually in the picture. That's a part of the actual functioning. But of course, that was given in this problem, so I don't need to figure that out. So in this case, it makes sense just to ask that. So I don't know. What's your take? Do you think, hey, that's actually easier? I don't know yet on the test. Am I going to make you use the ICR method, or am I just going to say go find velocity of C? And if you want to use, if you like one method more than the other, then good for you. I'm not sure. We'll talk about that a little bit later. We'll see. It seems like we might need to do another problem, but just so that you know, this ICR concept is really a 16.6 question. So both 16.5 and 16.6 are about this kind of related motion question when they're connected. But 16.5 is just using the horizontal and vertical system of equations approach, and 16.6 is using the instantaneous center of rotation approach. My guess is we need to soak on this a little longer. But I think I'll leave that up to you when we get back together on Tuesday, and you know, if you say, oh, I zipped right through those questions and I figured it out and now I got it. What that will mean is, well, we'll just get done a little early in class maybe. But I certainly don't. I'd rather go slow and have you kind of think you understand it. My gut reaction is I think it'd be cool for me to give you a question like this on Tuesday and just say, see if you can do it both ways and see if you can get the same answer both ways. Like, let's take the time to do that. And then we'll go on and talk about acceleration or whatever's next. That's my thought, but. All right.
See y'all.
See y'all.
Well, that made a lot more sense than Tuesday. So
Yeah, take some time.
all right, see you, Doug.
See you later, Landon.
I actually have a quick question. When we did a question 52, and you made a statement, velocity of B equals velocity of A plus velocity of BA, right?
Yes.
Okay. And in the end, we know all of the velocities, right?
Yeah, I'm going to pull that back up just so we can stare at what I wrote in case that helps us. Nothing but time here. Let's just take our time and make sure we get this. Okay.
Yeah. So and our velocity b equals 4.19.
Yeah.
Velocity of BA 4.51, and velocity of A equals 5.
Correct.
So
So let me say this. Do you understand that this velocity of B here in the picture is really is actually an important number in the sense that it's telling us how fast this thing is actually rotating. And that's how we talk about, again, think of it as a car going around a corner. Like that velocity of B right there, 4.19, is the speed. Right now, the point on the circle right here is here. You know, as it spins around here, that's one way of talking about the speed of that point. There's two ways. One of them is what's its linear speed. The other is what's its rotational speed. But I know that speed, that's actually a genuine speed, like 50 miles an hour or something like that. This velocity over here, though, is a little weirder. It's a little weirder because, you know, there's no points actually going in this direction. Does that make sense? So in a sense, although we found a number for that, 4.51, it sort of does not make sense to stop there. It makes sense to continue on past that and use that to find the other angular version of it. Since that was B to A, we continued to here and got an angular speed. That makes a little bit more sense to continue to angular speed. Do you agree with that, or do you see why I say that?
yeah, it's just if you're gonna use those numbers and we're gonna stick into the equation on the top, you know, they're not gonna work.
Oh, I see what you're saying. Yeah. I like that. That's a great thought. Oddly, I've never been asked that question before. I mean, my gut answer to that is it works, but only if you break it into horizontal and vertical.
Oh, okay.
Um,
Oh, yeah, you're right. You're right.
and I know that's true, but a better question is like, well, why doesn't that work? Like, there it is. It's sitting there. It's a beautiful equation.
Yeah. Okay, so if we want to double check, we just have to break it apart into X and Y.
Yeah, that's the.
Okay.
Let's see, vectors. I think that works up there, but you have to make vectors out of them. I don't know how clear this is because this is something that took a long time for me to get my mind out of. Technically, I think these are vectors up here. I think that's why it doesn't work. In other words, and when you say they're vectors, you mean not only do they have a magnitude of 5 and 4.19 and 4.51, but they also have a direction. And so I think if I actually added those vectors head to tail, I think they would actually work. Let me think about that. So let's just play with that for a second. So if I drew a horizontal vector of 5, and notice I don't really know how long to draw that, so I'm just going to call that 5, okay? And so that's A, but now I'm going to add to that this velocity of B over A vector, and we just figured out that that was 4.51, correct? So I'm going to draw it a little shorter. And then what direction do I draw it? Well, I've got to be perpendicular to this line right here. That's the only thing I really know, right? Perpendicular to that. So I guess I'll just eyeball it and say, well, it's, notice my drawing up here, I'd say is not that good. Would you agree that's a little past perpendicular? It's not bad. It's good enough that my drawing was fine. But if I draw, I'm going to try to draw it a little more this direction, and I'm going to draw it a hair short. And so there's velocity of B 4.19. This is velocity of B as it rotates around A. This was the velocity just of A itself. And so the question is kind of a ding, ding, ding. Is this, that's what you get when you add them. So is that the velocity of B? Notice the answer is yeah. Look at it. It's like, it looks parallel to this up here. Oops, that wasn't the right command. Looks parallel to that, doesn't it? And if I drew this in AutoCAD and actually measured the angles correctly, would I actually get 4.19 for that length? I think I would. Notice it. I think I wrote the wrong number there. This is supposed to be 4.51, but notice that actually does look a hair shorter, even just as a sketch, and it even looks like it's going the right direction. So. And so, why were those vectors and not scalars? Well, that's because they were representing, motion of something, which the direction of which has to be included. So that's a fantastic question.
Okay, now I'm feeling better about this.
It's one of the things I really enjoy about teaching because I try to be honest with you guys about this stuff. Like, I didn't know the answer to your question. I just thought, notice the funny thing is like, but if you go down to X's and Y's, does it make sense? That's what vectors do, is they keep track of X's and Y's. And so that's why it works in the horizontal and vertical case, but sort of not up here. And yeah. Nice question.
Okay. Thank you, Doug.
Yeah. I will see you tomorrow.
Yeah. So do we have to do 16.6 section?
I would say no. I don't think we practiced it enough. If we play with it a little more on Tuesday and you give it to me later, that's fine. If you find yourself being able to do it and want to get it done, go ahead. But I'd say I'd rather just 16.5 is due and the other one's like flexible.
Okay. All right. I'm going to go eat lunch for sure.
Sounds good. See you, my
Yep.
friend.
See ya.